Students, in this video we'll discuss properties of covariant differentiation. Let's recall that covariant differentiation takes tensors of order Mn. We have M covariant, those are the covariant terms, into m plus 1 n. So it raises the overall order of a tensor, okay? And the basic idea is the following. If I do the covariant derivative of a contravariant component, say bj, I will do partial bj, partial xi, and then plus, for covariant components, gamma of, we want the j in the bottom, right? So I have an i, then a j, then an m, then a b, m like that. Whereas for covariant components, you'd have this rule over here. Bj would be partial bj, partial xi minus gamma. I have an I downstairs, I need an M upstairs, and a J downstairs, and then a B, M like so. So that's the rules for how we do covariant differentiation of a contravariant vector for covariant differentiation of a covariant vector, okay? Excellent. And so now what are the basic rules of these things? So there are two basic rules. So here's basic rule number 1. Covariant differentiation is linear. Okay. In other words, if we had, let's say if tau was a tensor, I'll call this tensor of order Mn, and if sigma, if both tau and sigma are tensors of order m and n, and lambda, let's say an alpha and beta are real numbers, then this implies that alpha sigma plus beta tau is a tensor of order m plus 1 n. No, I'm just kidding, just mn, right? And of order mn. And the covariant derivative of this thing, of alpha sigma plus beta tau, is alpha, the covariant derivative of sigma, plus beta, the covariant derivative of tau. And that's trivial to prove just because both differentiation over here is linear, and this is a summation over here, and summation is also linear. So I have the sum of two linear operators. The sum of two linear operators is again linear, therefore covariant differentiation is a linear operator. Excellent. And of course, both these things are going to be of order m plus 1. That's what I was referring to earlier. And so now what's the next thing we want to do? We want to show there's a product rule, right? So what's the product rule going to be? Is valid. Okay? And now I'm not going to prove the product rule in general. I'm just going to show the general principle how you would prove it, right? So if I was to do the covariant derivative of a, let's say, of a just a covariant and then a contravariant, let's see what this would be by definition. Well, by definition, this would be partial bj, bk, a, j, and then partial xi. And then what? And then it would be a minus gamma I, j, m, a, m, b, k, plus gamma of I, that's the covariant, and now I'm going to do the contravariant, so I, m, and then a k, and then a, j, and then a b, m, like so. Okay, that's the definition of covariant differentiation. Now all I got to do is the product rule, right? So by the product rule, this is going to be a, j, partial bk, partial xi. I'm going to group that term, and then I'll put, well, let's do the product rule carefully, right? B, k upper, and then the k is upper here, so I have to be a little more careful about this indexing. That's an upper k. B upper k, partial daj lower, dxi, and then minus gamma m I j a m bk plus gamma k I m a j b m, right? And so now what are these terms together? So now we're in exactly our right position. So this term over here, this term over here, and this term over here both have a factor of aj. So that's going to be equal to aj, and then what's left over is going to be the covariant derivative of these bk terms, right? So that's going to be the I derivative of bk. And then these terms over here are just what have a bk in common, so plus bk. And then what? The I covariant derivative of a what? Of aj. And that's exactly the product rule. Now, of course, I've only proved this for a specific case, but the whole result, basically, this argument works in general, right? There's more terms involved in your sum, so you're going to end up with multi-index sums to prove this on. Okay, so that's the product rule. So in other words, we have what we expect to be true. Covariant differentiation is linear. Covariant differentiation satisfies the product rule. And there's one more remarkable property of this covariant differentiation. It's how it works with the metric tensor, right? And so what we're going to get over here is we're going to say that the covariant derivative of the metric tensor, g, j, k, is equal to 0. Okay, that's a beautiful property over here of covariant differentiation, is that the metric tensor has 0 covariant derivative. Okay, let's prove it. So what's this going to be equal to? Well, it's going to be equal to partial g, j, k, partial xi, and I have two covariant components, so both of those get negative. So negative gamma I, j, m, and then we're going to have a g, m, k, like that. And then a minus gamma I, k, m, g, j, k, like that. And the that k is going to turn to an m, actually. So that's going to be an m. GJM, GJM. Beautiful. Now, write what these Christoffel symbols are. So this expression over here is equal to partial g, jk, partial xi, and then minus gmk. Now, what's the definition of partial this Christoffel ijm? So by definition, that is going to be what? That is going to be 1/2, and then a gmk. Whoopsies, I need a different index now. I've already used k, so I have to use a different dummy index over here. Let's say gmq for dummy index. And then what? And then partial g I with respect to q. So I q partial x j plus. All right, excellent. And then plus partial g, then we have a jq partial xi, then minus partial gij partial xq, like that. That's what that Christoffel symbol is. And we have a minus one, then these terms over here, minus g jm times 1/2, and then g what? This is a Christoffel m upstairs, so m and then q, and then partial g, and then iq partial xk, plus partial g partial kq partial xi, and then finally minus partial gik partial xq. All right, so hopefully somehow all this vanishes, right? And so do this carefully. And so what are we going to get over here? So these terms over here are going to combine to give me a delta kq, delta kq. And these terms down over here, without that 1/2, are going to be a delta jq, delta jq. So everywhere we see a q up here, we're going to replace with a k. So that's going to be a k, that's going to be a k, and that's going to be a k over there. All right? Excellent. And then over here, wherever we see a j, we're going to replace it with a q. Wherever we see a q, we're going to replace it with a j. That's going to be a j. Whenever we see a q, replace it with a j. And there's a q, replace it with a j. Okay? Excellent. And so now what do these terms look like? Well, let's look at all the terms. So let's see what we're going to have over here. So let's look at the terms that cancel. So let's see over here. We have a delta. Let's look carefully. Okay. So we have a delta ijk. That's a delta ijk. And where else do we see a delta ijk? We see a delta ijk right over here, right? These terms over here are what? This was a what? That's a minus, that's a plus. So those terms over there are the same but opposite. So those terms cancel out. Great. We also have a delta what? We also have a delta ikj. So the delta ikj is over where? The delta ikj is over here. Okay, that's a negative. And I have a delta ikj over here with a what sign? With a positive sign. So these terms are negative, those terms are positive. Those terms are going to cancel out, right? And all we're left with is a what? All we're left with is a minus 1/2 of, so this is partial gjk partial xi minus 1/2 on this first term of partial gjk partial xi. And then down over here we have a what? Those terms survive over here. Those are a minus 1/2 of a partial gkj partial xi. But the metric is symmetric, so gjk and gkj are the same, so these terms all are the same, and so this gives me a total of 0, right? So in other words, the covariant derivative of the metric tensor has to vanish, right? And this is a beautiful property, which means it basically stems from the fact that when we start to talk about things like parallel transport, that when you parallel transport, you want to make sure that you're preserving the length of a vector relative to the overall frame, right? So there's a deeper geometric meaning behind the fact that simply just this derivative happens to be 0, right? It's designed in the metric is designed in a very special way, and covariant differentiation is designed in a special way so that you preserve sort of the geometric flavor of things when you start to do more, when you start to move along a curved surface where you're preserving the sort of different invariants. Thank you very much.